Right now, as you listen to these words, something extraordinary is happening beneath your feet. 6,000 kilometers down, deeper than you could dig in 1,000 lifetimes, iron crystals the size of office buildings are slowly growing and dissolving in temperatures that match the surface of the Sunday. These crystals have been forming and reforming for billions of years, spinning in a molten sea of metal that generates the invisible shield protecting every living thing on Earth's surface. This is Earth speaking in a language older than life itself. The ground beneath you feels solid, permanent, unchanging. But here's what's really happening. You're standing on the thin, cool skin of a planet that's alive with motion. The rock beneath major cities moves sideways at the speed your fingernails grow. Mountain ranges rise and fall like slow-motion waves. Ocean floors spread apart, creating new crust while old crust disappears into trenches so deep they could swallow Mount Everest with kilometers to spare. We exist in a universe where the most familiar thing in our lives, who in mind, the solid earth we walk on every day, turns out to be one of the most mysterious objects we've ever tried to understand. For most of human history, we had no idea. Ancient Greek philosophers noticed seashells embedded in rock on mountaintops and wondered how ocean creatures ended up so far from the sea. Some guessed correctly that the land had once been underwater, but they had no way to imagine the true scale of what was happening. They couldn't picture continents drifting across the planet's surface, colliding and separating in an endless, patient dance that's been going on for billions of years. The questions started small, as the best questions always do. Why do rocks sometimes contain the remains of sea creatures? Why do certain types of stones seem to attract iron? Why do earthquakes happen in some places but not others? Each question led to more questions, and gradually humanity began to realize we were living on something far stranger and more wonderful than anyone had imagined. Here's what makes Earth's mysteries so captivating. Every time we answer one question, we discover 10 new ones hiding in the shadows. When scientists first figured out that earthquakes were caused by moving rock, they discovered that the entire surface of the planet is broken into massive pieces called tectonic plates. When they mapped where earthquakes happen most often, they found those locations trace out the boundaries of these plates with stunning precision. But this discovery immediately raised new questions. What makes the plates move? How fast do they move? What happens when they collide? The answers revealed an Earth that's far more dynamic than anyone suspected. The plates don't just sit there. They slide over, under, and past each other in a complex choreography powered by heat from Earth's interior. Some boundaries are pulling apart, creating new ocean floor. Others are pushing together, building mountain ranges that grow millimeter by millimeter each year. Still others slide past each other, storing up tension that eventually releases in earthquakes. But here's where the mystery deepens. The engine driving all this motion lies in places no human has ever seen and never will. The Earth beneath us has layers like an onion, each one radically different from the others. We live on the crust, a thin shell of relatively cool rock that averages just 30 kilometers thick on land. If Earth were the size of an apple, the crust would be thinner than the apple's skin. Beneath the crust lies the mantle, nearly 3,000 kilometers of rock so hot it flows like thick honey over millions of years. Below that sits the outer core, 2,000 kilometers of liquid iron and nickel spinning around a solid inner core of crystallized metal. Each layer holds secrets that have taken decades to decode, and many remain mysteries today. The deepest humans have ever drilled is just over 12 kilometers, barely scratching the surface. Everything we know about Earth's interior comes from reading the planet's own signals. Earthquake waves that travel through different materials at different speeds, magnetic fields generated by moving metals, and subtle variations in gravity that reveal hidden structures far below. These signals tell us remarkable stories. The solid inner core, discovered less than a century ago, spins independently of the rest of the planet. It rotates slightly faster than Earth's surface, gaining about 1/3 of a degree per year. Scientists know this because they can track how seismic waves change as they pass through the core over time, watching the inner core's structure slowly rotate relative to the surface. But recently, something changed. Around 2010, the inner core began slowing down. Now it might even be rotating slower than the surface. No one knows why. This is typical of Earth's mysteries. Just when we think we understand something, the planet surprises us. The magnetic field that protects us from deadly radiation streaming from the sun emerges from the churning motion of liquid iron in the outer core. This field isn't steady, it fluctuates constantly, and every few 100,000 years it completely reverses. North becomes south, south becomes north. We know this because iron minerals in ancient rocks preserved the direction of the magnetic field when they formed, creating a historical record of these reversals stretching back millions of years. Right now, the magnetic field is weakening. It's lost about 5% of its strength in the past century. The magnetic North Pole is wandering across the Arctic at accelerating speeds, moving from northern Canada towards Siberia at about 50 kilometers per year. Some scientists think we might be heading toward another reversal, but no one knows when it might happen or how long it would take. During past reversals, the magnetic field didn't disappear entirely, but it became much weaker and more chaotic. Multiple north and south poles appeared and moved around before settling into their new positions. These periods of magnetic chaos might have lasted thousands of years. What would happen to life on Earth during a magnetic reversal? We're not entirely sure, because no modern technological civilization has ever experienced one. The atmosphere that gives us breath and shields us from space is itself a mystery wrapped in more mysteries. We know that early Earth had almost no oxygen. The atmosphere was mostly nitrogen, carbon dioxide, water vapor, and other gases that would be toxic to most life today. Then, about 2.5 billion years ago, something extraordinary happened. Tiny organisms called cyanobacteria evolved the ability to capture energy from sunlight and split water molecules, releasing oxygen as waste. This was one of the most catastrophic pollution events in Earth's history. Oxygen was toxic to most life forms that existed then. It caused a mass extinction that wiped out countless species. But it also made possible the evolution of complex life forms that could use oxygen to power their cellular engines. Without this ancient environmental disaster, we wouldn't exist. The oxygen revolution turned Earth's oceans red with rust as the gas reacted with dissolved iron, creating distinctive red and black banded iron formations that geologists can still see in rocks from that era. It changed the chemistry of the atmosphere, the oceans, and the surface rocks. It even affected space around Earth, because oxygen in the upper atmosphere forms ozone, which blocks harmful ultraviolet radiation from the sun. Yet we still don't fully understand how cyanobacteria first evolved photosynthesis, or why it took nearly 1 billion years for atmospheric oxygen levels to rise significantly after photosynthesis first appeared. The oceans themselves harbour mysteries that seem to multiply the deeper we look. We've mapped less than 20% of the ocean floor in detail, even though water covers 70% of Earth's surface. The deepest parts of the oceans remain as unexplored as distant planets. The Mariana Trench plunges 11 kilometers below sea level, deeper than Mount Everest is tall. At the bottom, water pressure exceeds 1,000 times atmospheric pressure at sea level. Yet life thrives even there, in forms unlike anything found anywhere else on Earth. Around volcanic vents on the ocean floor, where superheated water rich in minerals erupts from cracks in the crust, entire ecosystems exist without any energy from the sun. Giant tube worms with no digestive systems rely on bacteria living inside them to convert chemicals from the vents into food. Fish with antifreeze proteins in their blood swim in water that should be too cold for them to survive. Microbes live in conditions of temperature, pressure, and chemistry that would instantly kill most surface life. These deep-sea communities have forced scientists to completely rethink what life needs to survive and where it might exist elsewhere in the universe. If life can thrive in Earth's deep ocean trenches, it might also exist in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. But here's what's truly mind-bending about Earth's mysteries. They're all connected in ways we're only beginning to understand. The magnetic field generated in the core affects the atmosphere. Solar wind particles, deflected by the magnetic field, create the auroras that dance across polar skies. The movement of tectonic plates affects ocean circulation patterns, which influence climate around the world. Volcanic eruptions can change atmospheric chemistry for years, affecting plant growth and animal migration patterns on continents thousands of kilometers away. Earth operates as a single integrated system where every component influences every other component in ways both obvious and subtle. Change one part, and eventually the effects ripple through the entire planet. This interconnectedness makes Earth's mysteries even more fascinating and important. When we try to understand how climate has changed in the past, we need to know about ice sheets, ocean currents, atmospheric chemistry, volcanic activity, changes in Earth's orbit, and the behavior of the magnetic field. When we study mass extinctions, we discover that they often coincide with massive volcanic eruptions, asteroid impacts, changes in sea level, or other planetary scale events. Every rock, every fossil, every ice core sample from Antarctica, every measurement of the magnetic field contains clues about how this planetary machine operates. Scientists have become detectives, reading Earth's autobiography written in stone and ice and metal, trying to understand the story of our home. And that story keeps getting stranger. Recent discoveries have revealed that Earth's interior is far more complex than anyone suspected. There are structures deep in the mantle that are older than complex life on the surface. There are regions where the normal rules of physics and chemistry are pushed to their limits. There are processes happening in Earth's core that we can detect but cannot yet explain. We've learned that continents don't just drift randomly, they seem to follow long-term cycles, periodically assembling into supercontinents and then breaking apart again. We've discovered that the oxygen levels in Earth's atmosphere have fluctuated dramatically throughout history, sometimes rising so high that wildfires would have been almost impossible to extinguish, other times dropping so low that large animals couldn't survive. We've found evidence that Earth has experienced periods when ice covered the planet from pole to equator, creating a snowball Earth that nearly ended life's story before it really began. We've learned that massive volcanic eruptions have repeatedly changed the planet's climate and triggered mass extinctions. We've discovered that asteroid and comet impacts have shaped not just life's evolution, but the very structure of the continents and oceans. Each discovery reveals new layers of complexity in Earth's story. Each answered question opens doors to rooms full of new mysteries. Modern technology has given us tools that would seem like magic to earlier generations of Earth explorers. Satellites measure the movements of continents with millimeter precision. Seismometers detect earthquake waves so small they would be invisible to our senses, using those waves to create three-dimensional images of structures thousands of kilometers underground. Mass spectrometers can identify individual atoms in rock samples billions of years old, revealing the conditions under which those rocks formed. Yet even with these remarkable tools, Earth keeps its deepest secrets. We still don't know exactly how the magnetic field forms, or why it reverses. We can't predict when or where the next major earthquake will strike. We don't understand why some volcanoes erupt predictably, while others remain quiet for thousands of years before exploding without warning. The questions that started with ancient Greeks wondering about seashells on mountaintops have led us to a profound realization. We live on a planet that's far more mysterious, more dynamic, and more interconnected than our ancestors could have imagined. Earth is not just our home, it's an active, evolving world where the ground beneath our feet participates in processes that span billions of years and shape the future of life itself. The whispers from this living world are growing louder as our ability to listen improves. Each new instrument, each new technique for reading Earth's signals reveals more of the conversation that's been going on beneath our feet for longer than life has existed. And this is just the beginning of the story. 4.5 billion years ago, in a disk of cosmic dust and violence that would have been unrecognizable as the birthplace of our world, Earth began asking its first questions. But these weren't questions posed by curious minds. They were questions written in fire and ice, in collision and creation, in the very atoms that would eventually become everything we know. Picture this: a young sun, barely stable, blazing in the center of a swirling disk of debris left over from stellar formation. Within this disk, countless fragments of rock and ice and metal are colliding, sticking together, growing larger through a process so chaotic it seems impossible that anything as organized as a planet could emerge from it. But here's what's really happening in that ancient chaos. Gravity is asking the first question Earth would ever face. How do you build a world from scattered pieces? The answer came through violence on a scale that defies imagination. Planetesimals, chunks of rock the size of mountains, slammed into the growing Earth at speeds of tens of kilometers per second. Each impact released energy equivalent to millions of nuclear weapons, melting and vaporizing rock, creating a hellish ball of molten stone surrounded by an atmosphere of vaporized metal and rock. The early Earth was nothing like the world we know. It spun much faster, completing a day in just 6 hours. It had no moon, no oceans, no atmosphere capable of supporting life as we understand it. The surface temperature exceeded 1500 degrees Celsius, hot enough to melt copper. Any water that existed would have been instantly vaporized into steam. Yet even in this infernal environment, Earth was already developing the characteristics that would eventually make it a haven for life. The planet's size was just right, large enough to hold onto an atmosphere through gravity, but not so large that it would trap deadly gases like Venus or become a gas giant like Jupiter. Its distance from the Sun placed it in what astronomers now call the habitable zone, where liquid water could eventually exist on the surface. But first, Earth had to survive its most traumatic experience, the birth of the Moon. About 50 million years after Earth's formation, when our planet had grown to roughly its current size but was still mostly molten, something extraordinary happened. A Mars-sized object that astronomers call Theia struck Earth in a glancing blow that nearly shattered both worlds. The impact was so violent it vaporized Theia and blasted enormous amounts of material from Earth's outer layers into space. This collision fundamentally changed Earth's character. The impact tilted our planet's axis, giving us seasons. It stripped away much of Earth's early atmosphere and added material from Theia to our world's composition. Most importantly, the debris from this cosmic catastrophe eventually coalesced to form the Moon. The Moon's formation wasn't just an interesting astronomical event, it was essential to making Earth a world where complex life could evolve. The Moon's gravitational pull creates tides that may have helped concentrate the chemicals needed for life in tidal pools. It stabilizes Earth's axial tilt, preventing dramatic climate swings that would make long-term evolution difficult. And in Earth's early history, when the Moon was much closer than it is today, it created tides hundreds of meters high that stirred the oceans and atmosphere in ways that may have been crucial for early life. After the moon-forming impact, Earth faced another fundamental question. Where would the water come from? This question puzzled scientists for decades. The inner solar system, where Earth formed, was hot enough that most water would have been vaporized. Yet Earth today is covered with oceans containing more than 1 billion cubic kilometers of water. Where did all this water originate? The answer appears to involve multiple sources, each contributing to the mystery of Earth's transformation from a molten ball of rock to a water world. Some water was already present in the minerals that formed Earth, trapped within crystal structures and released as the planet cooled. But much of it may have arrived later, delivered by asteroids and comets from the outer solar system during a period called the Late Heavy Bombardment. Between 4.1 and 3.8 billion years ago, Earth endured a cosmic shooting gallery. Asteroids the size of Texas slammed into the planet's surface, creating impact craters larger than entire countries. Many of these asteroids contained ice and organic compounds that had formed in the cold outer reaches of the solar system. Each impact simultaneously brought destruction and the building blocks of future life. The evidence for this bombardment is written on the Moon's surface, where ancient craters remain preserved because there's no atmosphere or tectonic activity to erase them. Earth would have received even more impacts than the Moon due to its larger size and stronger gravity, but most traces of these ancient collisions have been erased by billions of years of geological activity. As Earth cooled and water accumulated, the planet faced its next great question. How do you create an atmosphere that can support life? The early atmosphere contained virtually no oxygen. Instead, it was dominated by water vapor, carbon dioxide, methane, ammonia, and other gases that would be toxic to most modern life forms. Lightning crackled through these alien skies, and ultraviolet radiation from the sun bathed the surface with deadly intensity because there was no ozone layer to block it. Yet somewhere in this hostile environment, about 3.8 billion years ago, life appeared. The first organisms were simple, just single cells without even a nucleus to contain their genetic material, but they possessed something revolutionary: the ability to reproduce and evolve. For nearly 1 billion years, these primitive life forms dominated Earth, slowly changing the chemistry of the oceans and atmosphere. Then, about 2.7 billion years ago, some of them evolved a capability that would transform the entire planet: photosynthesis. Here's what makes this development so remarkable. The first photosynthetic organisms didn't just figure out how to capture energy from sunlight. They learned to split water molecules to get the hydrogen they needed, releasing oxygen as a waste product. This was Earth's first major pollution crisis, and it nearly ended life's story before it really began. Oxygen was toxic to most life forms that existed then. It reacted with iron dissolved in the oceans, creating massive rust deposits that turned the seas red. It attacked organic molecules essential for cellular function. It caused what scientists call the Great Oxygenation Event, but it might be more accurately described as the Great Oxidation Catastrophe. For hundreds of millions of years, oxygen levels in the atmosphere remained low as the gas reacted with iron and other chemicals on Earth's surface. But gradually, oxygen began to accumulate in the atmosphere. By 2 billion years ago, atmospheric oxygen had reached levels that could support more complex forms of life. The consequences were profound. Oxygen made possible the evolution of organisms that could use this reactive gas to power much more efficient cellular engines. These new life forms could extract far more energy from their food than their oxygen-hating predecessors. They could grow larger, move faster, and develop more complex structures. But the oxygenation of Earth's atmosphere also set the stage for one of the most mysterious episodes in our planet's history: Snowball Earth. About 700 million years ago, Earth experienced a climate catastrophe so severe it nearly extinguished life entirely. Ice sheets spread from the poles toward the equator, reflecting more and more sunlight back to space, causing further cooling in a runaway, the process that eventually covered the entire planet in ice from pole to pole. Imagine Earth as a giant snowball spinning through space, with ice sheets kilometers thick, covering even the tropical oceans. Temperatures at the equator dropped to minus 40 degrees Celsius. The only liquid water on the planet existed beneath the ice sheets, or around volcanic hotspots. How did life survive this frozen hell? That's still one of Earth's greatest mysteries. Scientists think some organisms may have survived in pockets of liquid water around volcanic vents, or in thin films of water between ice and rock. Others might have endured by entering a kind of suspended animation, waiting for conditions to improve. The fact that complex life exploded in diversity shortly after Snowball Earth ended suggests that somehow enough organisms survived to repopulate the planet when the ice finally melted. But what ended the Snowball Earth period? The answer involves one of Earth's most important recycling systems, the carbon cycle. Even when the planet was frozen, volcanoes continued to erupt, pumping carbon dioxide into the atmosphere. Normally, this carbon dioxide would be removed from the atmosphere by chemical reactions with rocks exposed to air and water. But on a frozen planet, these reactions slowed dramatically while volcanic emissions continued. Over millions of years, carbon dioxide built up in the atmosphere until the greenhouse effect became strong enough to begin melting the ice. Once the melting started, it accelerated rapidly. Dark ocean water, exposed as ice melted, absorbed more heat than reflective ice. The planet swung from being completely frozen to being extremely hot in a geological instant, perhaps just a few thousand years. The end of Snowball Earth set the stage for the most spectacular burst of evolutionary innovation in Earth's history, the Cambrian explosion. About 540 million years ago, in just 20 million years, a blink of an eye. In geological terms, I've invented virtually every major body plan that exists today. Eyes appeared for the first time, along with shells, claws, spines, and sophisticated predator-prey relationships. Animals developed the ability to burrow, swim, crawl, and filter feed. The fossil record from this period reveals an explosion of creativity that still baffles scientists. Before the Cambrian explosion, most life consisted of simple, soft-bodied organisms that left few fossils. The Ediacaran fauna that preceded the Cambrian period included some large, complex organisms, but they were unlike anything alive today, mysterious forms that may represent evolutionary experiments that ultimately failed. Then, suddenly, the fossil record fills with creatures that look recognizably modern. Arthropods with jointed legs and compound eyes, mollusks with shells, early vertebrates with primitive backbones. It's as if life learned to construct complex, durable bodies almost overnight. Why did this evolutionary explosion happen when it did? Scientists have proposed many explanations. Rising oxygen levels may have finally reached concentrations that could support larger, more active animals. The end of Snowball Earth may have opened up new ecological niches. The evolution of predation may have triggered an arms race that drove rapid innovation in both offensive and defensive capabilities. But the ultimate cause of the Cambrian explosion remains one of evolution's greatest mysteries. What we do know is that it established the basic patterns of animal life that persist today, more than 500 million years later. Throughout all these dramatic changes, Earth's geological processes continued to reshape the planet's surface. The first supercontinents assembled and broke apart. The oldest rocks that survive today formed during this period, preserving evidence of Earth's early atmosphere and oceans in their mineral compositions and isotopic signatures. These ancient rocks tell stories of a world almost alien in its strangeness. They contain evidence of massive volcanic eruptions that covered areas larger than entire modern countries with lava. They preserve chemical signatures of oceans with radically different compositions than today's seas. They record changes in atmospheric chemistry that reveal the co-evolution of life and environment over billions of years. By the end of this early phase of Earth's history, our planet had established the basic systems that continue to operate today. Plate tectonics was reshaping the surface, moving continents and creating ocean basins. The water cycle was transporting materials between the atmosphere, oceans, and land. The carbon cycle was regulating climate through complex feedbacks between biological and geological processes. But Earth was just getting started. The questions posed by our planet's early history — how do you build a world? Where does water come from? How do you create a life-supporting atmosphere? — had been answered. But those answers had created entirely new questions that would drive Earth's continuing evolution. The stage was set for the next great chapter in Earth's story, the rise of complex life and the discovery of the processes that had shaped our world. But first, life would have to survive several more near-extinction events, and Earth would have to complete its transformation from an alien world to the planet we recognize today. The giants that walked during Earth's early history weren't living creatures. They were continent-sized glaciers, asteroid impacts that reshaped entire hemispheres, and volcanic eruptions that changed the composition of the atmosphere. But their footprints remain visible today in the rocks beneath our feet, the water in our oceans, and the oxygen in our lungs. Every breath you take contains atoms of oxygen produced by ancient cyanobacteria during the Great Oxygenation Event. Every drop of water you drink may have been delivered to Earth by comets during the Late Heavy Bombardment. Every step you take crosses ground that has been frozen, melted, submerged, uplifted, and transformed countless times over billions of years. The questions Earth asked during its youth, questions written in fire and ice, in creation and catastrophe, questions shaped not just our planet's physical characteristics but the very possibility of our existence. We are here because Earth found answers to seemingly impossible challenges, because our planet proved remarkably resilient in the face of cosmic violence and climate catastrophe. But the story of how we discovered these answers, how we learned to read the record of Earth's early history preserved in rocks and fossils and ice, is just as remarkable as the history itself. That story begins with curious observers who noticed patterns in stones and wondered what they might mean, the first humans to realize that Earth itself was keeping a diary of its extraordinary past. In 1837, a young Swiss naturalist named Louis Agassiz stood at the edge of a glacier in the Alps and saw the truth. Around him stretched a landscape that didn't match the gentle explanations his professors had offered for how valleys formed. The rocks were scarred with parallel scratches. Massive boulders sat where no river could have carried them. The valley walls showed polishing that no flood could have created. Agassiz realized he was looking at the fingerprints of ice, evidence that massive glaciers had once carved these valleys with the slow, irresistible force of moving mountains. This moment launched an age of discovery, where geologists learned that Earth itself had been keeping a detailed diary for billions of years, written in a language of stone and crystal, fossil and mineral. Every rock layer became a page in Earth's autobiography. Every fossilized shell a sentence describing ancient seas, every grain of sand a word in stories that spanned eons. But learning to read this diary required a revolution in human thinking. For centuries, most people believed Earth was only a few thousand years old. The idea that rocks could preserve evidence of events millions or billions of years in the past seemed impossible. Mountains, valleys, and ocean basins were thought to be essentially unchanged since creation. The discovery that Earth had a deep history, and that this history was written in the very ground beneath our feet, challenged fundamental assumptions about time, change, and our place in the natural world. The key insight came from understanding that the same processes we see operating today have been shaping Earth throughout its history. Rivers carve canyons grain by grain. Volcanoes build mountains eruption by eruption. Glaciers sculpt landscapes 1 millimeter at a time. Given enough time, far more time than human civilization had imagined, these gradual processes could create the grandest features of Earth's surface. This principle, called uniformitarianism, opened the door to reading Earth's ancient history. If we understand how rocks form today, we can interpret rocks that formed millions of years ago. If we know how fossils are preserved in modern sediments, we can decode the stories told by fossils in ancient rock layers. The stories those rocks told were astounding. Limestone formations in the heart of continents revealed that vast seas had once covered areas that are now dry land. Coal deposits showed that ancient swamps had flourished where polar ice now dominates. Fossil seashells found on mountaintops confirmed what Agassiz and others suspected. The surface of Earth had been constantly changing, with ocean floors becoming mountain peaks and coastal plains sinking beneath the waves. But the most revolutionary discovery came from the careful study of rock layers themselves. Geologists realized that rocks form in predictable sequences. Sedimentary rocks, formed from particles of sand, mud, and organic matter settling in ancient seas, lakes, and river systems, preserve the conditions that existed when they formed. By studying these layers, scientists could reconstruct not just where ancient shorelines existed, but what the climate was like, which organisms lived in those ancient environments, and how ecosystems changed over time. The principle of superposition, psi, that older rock layers lie beneath younger ones unless disturbed, provided a way to establish the relative ages of different formations. The principle of faunal succession, Qi, that different time periods are characterized by distinctive fossil species, allowed geologists to correlate rock layers across vast distances and create a timeline of Earth's history. This timeline revealed a planet with a history far stranger and more dramatic than anyone had suspected. The geological record showed evidence of repeated mass extinctions, when most species on Earth vanished forever. It preserved signs of ice ages when glaciers covered much of the northern hemisphere. It contained proof of times when the climate was so warm that forests grew near the poles and coral reefs flourished in what is now the Arctic Ocean. But perhaps the most mind-bending revelation was the discovery that the very arrangement of continents and oceans had changed throughout Earth's history. In 1912, a German meteorologist named Alfred Wegener proposed that the continents had once been joined together in a single supercontinent that he called Pangaea. His evidence was compelling but circumstantial. Similar fossils found on continents now separated by thousands of kilometers of ocean, matching rock formations on opposite sides of the Atlantic, and the obvious puzzle piece fit between the coastlines of Africa and South America. Wegener's idea of continental drift was ridiculed by most geologists of his time. They couldn't imagine a mechanism powerful enough to move entire continents across Earth's surface. The idea seemed to violate everything known about the strength and rigidity of rocks. The vindication of Wegener's vision came from an unexpected source, the bottom of the ocean. During World War II, improved sonar technology allowed scientists to map the ocean floor for the first time. What they discovered revolutionized our understanding of Earth's dynamics. The ocean floor wasn't flat and featureless as expected. It contained vast mountain ranges, deep trenches, and patterns of ridges and valleys that seemed to follow systematic rules. The most important discovery came from a remarkable woman, whose work initially received little recognition. Marie Tharp, working at Columbia University in the 1950s, spent years carefully plotting depth measurements from research ships to create the first detailed maps of the Atlantic Ocean floor. In 1957, Tharp made a discovery that changed geology forever. Her pencil traced across the map she was creating, following a chain of underwater mountains that ran down the center of the Atlantic Ocean like the seam on a baseball. This mid-Atlantic ridge wasn't just a mountain range. It was a crack in Earth's crust where new ocean floor was being created. Here's what Tharp had discovered. The ocean floor spreads apart at mid-ocean ridges as molten rock rises from Earth's interior, cools, and forms new crust. This process, called seafloor spreading, pushes the existing ocean floor away from the ridge like a slow-motion conveyor belt. The Atlantic Ocean is growing wider by about 2 centimeters per year, as new crust forms at the mid-Atlantic ridge. But if new ocean floor is constantly being created, where does the old ocean floor go? The answer was found in deep ocean trenches, underwater canyons, where old ocean floor dives back into Earth's interior, completing a cycle of creation and destruction that has been operating for billions of years. This discovery provided the mechanism that had eluded Wegener. Continents don't plow through solid rock. They ride on massive plates of crust that move as the underlying mantle slowly convects, carrying heat from Earth's interior to the surface. The theory of plate tectonics, developed through the 1960s, explained not just continental drift but virtually every major feature of Earth's surface. Mountain ranges form where plates collide and crumple. Volcanoes mark spots where plates separate or where one plate dives beneath another. Earthquakes occur along plate boundaries, where motion is temporarily stuck but building towards sudden release. Even more remarkably, the magnetic properties of ocean floor rocks provided a way to measure the history of plate motion with unprecedented precision. As molten rock cools and solidifies at mid-ocean ridges, iron minerals in the rock align themselves with Earth's magnetic field, creating a permanent record of the field's direction at the time the rock formed. Scientists discovered that this magnetic signature creates a zebra-striped pattern on the ocean floor, alternating bands of normal and reversed magnetic polarity, stretching away from mid-ocean ridges. These magnetic stripes reveal that Earth's magnetic field has reversed hundreds of times throughout geological history, with north and south magnetic poles switching places every few 100,000 years on average. More importantly, the symmetrical pattern of magnetic stripes on either side of mid-ocean ridges provided direct evidence for seafloor spreading and allowed scientists to calculate exactly how fast different ocean basins have been expanding. But the revelations preserved in Earth's rocks weren't finished surprising us. In 1980, a father and son team of scientists, Luis and Walter Alvarez, made a discovery that would revolutionize our understanding of mass extinctions and Earth's vulnerability to cosmic catastrophes. They were studying the boundary between rock layers formed during the Cretaceous and Paleogene periods, LI, the geological, the moment when dinosaurs vanished from the fossil record 66 million years ago. In this thin layer of clay found at sites around the world, the Alvarezes discovered something extraordinary: concentrations of the element iridium that were hundreds of times higher than normal. Iridium is rare in Earth's crust, but common in asteroids and comets. The only reasonable explanation was that this layer preserved the debris from a massive asteroid impact. The implications were staggering. The dinosaurs, the dominant land animals for more than 160 million years, had been wiped out not by gradual climate change or volcanic activity, but by a cosmic catastrophe. An asteroid roughly 10 kilometers across had struck Earth with the force of billions of nuclear weapons, creating a global environmental disaster that ended the Mesozoic era in an instant. Finding the smoking gun took more than a decade, but in the 1990s, scientists identified the Chicxulub crater on Mexico's Yucatan Peninsula as the impact site. Buried beneath later sediments and partly hidden beneath the Gulf of Mexico, this crater is more than 180 kilometers across, every one of the largest impact structures on Earth. The asteroid impact story explained more than just the extinction of dinosaurs. It revealed that Earth's history has been punctuated by catastrophic events that reset the course of evolution. Without the asteroid impact that ended the Cretaceous period, mammals might never have diversified beyond small nocturnal creatures. The extinction of dinosaurs opened ecological niches that allowed our mammalian ancestors to flourish and eventually evolve into the complex forms we see today, including humans. This discovery launched a new field of study: catastrophism. Scientists realized that Earth's history includes both gradual change and sudden dramatic events that can reshape life and landscapes in geological instants. Massive volcanic eruptions, asteroid impacts, rapid climate shifts, and other catastrophes have repeatedly altered the course of Earth's development. The evidence for these catastrophes is written throughout the geological record, but learning to read it required new techniques and technologies that could decode increasingly subtle signals preserved in ancient rocks. Ice cores from Antarctica and Greenland provided year-by-year records of ancient climate extending back hundreds of thousands of years. Trapped air bubbles in the ice preserve samples of ancient atmospheres, revealing how carbon dioxide and other greenhouse gas concentrations have changed over time. Volcanic ash layers in the ice mark major eruptions and their effects on global climate. Isotope analysis of ancient shells and bones revealed the temperatures of ancient oceans and the diets of extinct organisms. Tree rings from ancient forests preserved detailed records of seasonal climate variations. Coral reefs in tropical oceans recorded changes in sea level and ocean chemistry with remarkable precision. Each new technique for reading Earth's historical record revealed additional layers of complexity in the story of our planet's development. Magnetic reversals recorded in rock layers showed that Earth's magnetic field has not only reversed many times, but has also varied dramatically in strength. During some periods, the magnetic field was much stronger than today. During others, it was so weak that Earth's surface received little protection from cosmic radiation. Seismic waves from earthquakes provided a way to image the interior of Earth with increasing detail. Scientists discovered that the mantle isn't uniform. It contains plumes of hot rock rising from near the core mantle boundary, regions of cold, dense rock sinking toward the deep interior, and mysterious structures that don't fit simple models of how the planet's interior should behave. The ocean floor revealed features that challenged every assumption about how Earth's surface evolves. Massive underwater landslides had swept across hundreds of kilometers of seafloor. Volcanic eruptions beneath miles of ocean water had created formations unlike anything seen on land. Deep-sea drilling projects brought up samples of ocean floor sediments that preserved detailed records of how ocean circulation, climate, and marine ecosystems had changed over millions of years. But perhaps the most remarkable discovery was that many of Earth's processes operate on multiple timescales simultaneously. The carbon cycle that regulates Earth's climate operates on timescales ranging from years to millions of years. Volcanic activity can change atmospheric chemistry within days or decades, but the deeper processes that drive volcanic activity operate over millions of years as mantle plumes rise and plates reorganize. Mountain building can uplift landscapes by millimeters per year, but the ultimate source of the forces that build mountains lies in mantle convection patterns that evolve over hundreds of millions of years. This discovery of multiple interconnected timescales helped explain why Earth's climate and surface features have remained relatively stable, despite dramatic changes in solar output, atmospheric composition, and continental configuration over billions of years. The planet operates as a self-regulating system, where changes in one component trigger feedback responses in other components, usually in directions that moderate rather than amplify the original change. Yet the same processes that provide stability can also lead to sudden transitions when pushed beyond critical thresholds. The end Permian mass extinction 250 million years ago, which eliminated more than 90% of marine species, appears to have been triggered when massive volcanic eruptions in Siberia released enough greenhouse gases to cause runaway climate change that acidified the oceans and depleted atmospheric oxygen. Learning to read, these stories written in stone required more than just new scientific techniques. It demanded a fundamental change in how humans think about time and change. The discovery that Earth has a deep history measurable in billions of years expanded our conception of time beyond anything human cultures had previously imagined. The realization that gradual processes can create dramatic results over geological time challenged intuitive notions about cause and effect. Most importantly, the ability to read Earth's historical record revealed that our planet is far more dynamic and changeable than it appears during a human lifetime. Continents drift, climates shift, sea levels rise and fall, magnetic poles reverse, and mass extinctions reset the course of evolution. What seems permanent and unchanging from a human perspective is actually part of an ongoing story of constant transformation. The revelations written in stone and preserved in ice have given us a new understanding of our place in Earth's story. We exist during a brief moment in a 4.5 billion year epic of planetary evolution. The ground beneath our feet has travelled thousands of kilometres from where it formed. The oxygen we breathe was produced by organisms that lived billions of years ago. The water we drink has circulated through countless ocean basins, ice sheets, and atmospheric cycles. But the story of Earth's deep history also revealed something unexpected. The processes that shaped our planet are still operating today, and we have become participants in that story rather than just observers of it. The same forces that have driven climate change, mass extinctions, and continental rearrangement throughout Earth's history continue to operate in the modern world. Understanding Earth's past became essential for understanding its present and predicting its future. The revelations written in stone provided both the foundation for modern Earth science and the context for recognizing that humanity has become a geological force capable of influencing planetary processes on the same scale as volcanoes, glaciers, and asteroid impacts. The detective work that began with Agassiz's recognition of glacial fingerprints in Swiss valleys had led to a complete revolution in our understanding of Earth and our relationship to it. But as the 20th century progressed, scientists developed tools that would allow them to observe Earth's processes in real time, rather than just reading their historical signatures. The age of directly watching our planet's mysterious processes had begun. Today's Earth explorers wield tools that would seem like magic to earlier generations of scientists. Satellites orbiting hundreds of kilometers above us measure the movement of continents with precision that would make a Swiss watchmaker envious. Deep beneath Antarctic ice, detectors the size of office buildings capture ghostly particles that have traveled through the entire planet without interacting with a single atom. In laboratories around the world, machines analyze individual crystals smaller than the width of human hair to reveal the conditions that existed when those crystals formed billions of years ago. We have entered an age where the invisible processes that drive Earth's evolution have become visible, where the undetectable forces that shape our planet can be detected and measured, where questions that puzzled scientists for centuries can be answered in real time. Here's what makes this technological revolution so remarkable. These tools don't just measure Earth's processes more precisely than before, they reveal entirely new aspects of how our planet works that previous generations of scientists never suspected existed. Consider the global positioning system satellites that have transformed how we navigate and communicate. Originally designed for military navigation, these satellites have become one of our most powerful tools for studying Earth's dynamics. By precisely measuring the time it takes radio signals to travel from satellites to receivers on the ground, scientists can determine the position of any point on Earth's surface to within millimeters. This precision has revealed that nothing on Earth's surface is truly stationary. North America is drifting away from Europe at about 2.5 centimeters per year, roughly the speed your fingernails grow. California is creeping northward along the San Andreas Fault at 5 centimeters per year. The Himalayan mountains continue to rise as India pushes into Asia, growing by about 1 centimeter annually. But GPS measurements have revealed far more subtle motions that no one anticipated. The solid ground beneath major cities rises and falls by several centimeters each year as groundwater is pumped out and refilled. Coastal areas rebound by millimeters per year as ice sheets that melted thousands of years ago continue to release their gravitational grip on the land. The entire North American continent tilts slightly as seasonal snow accumulates and melts. These tiny motions add up to dramatic changes over geological time, but before GPS, they were completely invisible to human observation. Now we can watch continental drift happening in real time, measuring the daily progress of processes that take millions of years to complete their work. Satellite radar has pushed this capability even further. Synthetic aperture radar satellites can detect ground movements as small as a few millimeters across areas hundreds of kilometers wide. These measurements have revealed that volcanoes begin inflating months or years before they erupt, as magma rises and pushes up the ground surface. Earthquake faults store strain that can be measured long before the fault ruptures catastrophically. The city of Los Angeles is being squeezed at a rate of about 7 millimeters per year, as motion on surrounding faults gradually builds toward future earthquakes. The Yellowstone caldera inflates and deflates like a massive, slow-breathing organism as magma moves in chambers miles beneath the surface. Iceland's volcanoes telegraph their intentions through ground movements that begin months before eruptions reach the surface. But perhaps the most remarkable achievement of satellite technology is the ability to measure changes in Earth's gravitational field from space. The Gravity Recovery and Climate Experiment satellites, launched in 2002, detect variations in gravity so subtle they reveal how mass is redistributed around the planet. As groundwater is pumped from aquifers, as ice sheets melt, as ocean currents shift massive amounts of water, these satellites measure the tiny changes in gravitational pull that result. This capability has revolutionized our understanding of Earth's water cycle. The satellites can measure how much water is stored in underground aquifers, track the seasonal accumulation and melting of snow and ice, and monitor how climate change is redistributing water around the planet. They've revealed that major aquifers in California, India, and the Middle East are being depleted much faster than previously realized, and that ice loss from Greenland and Antarctica is accelerating. The gravitational measurements are so precise that they can detect the mass of water vapor in the atmosphere, the weight of seasonal snow accumulation, and even the tiny changes in Earth's rotation that result from large earthquakes redistributing mass within the planet. But while satellites provide a global view of Earth's processes, other technologies allow scientists to peer deep into the planet's interior with unprecedented detail. Seismic tomography uses earthquake waves to create three-dimensional images of Earth's interior structure, much like medical CT scans create images of the human body. When earthquakes occur, they generate waves that travel through the entire planet at speeds that depend on the temperature, density, and composition of the materials they encounter. By analyzing earthquake waves recorded at thousands of seismic stations around the world, scientists can reconstruct detailed images of structures thousands of kilometers beneath the surface. These images have revealed that Earth's interior is far more complex and dynamic than anyone suspected. Rising plumes of hot rock, some originating near the core mantle boundary, 3,000 kilometers down, create the volcanic hotspots that built Hawaii, Iceland, and Yellowstone. Slabs of cold, dense ocean floor sink deep into the mantle after being subducted at ocean trenches, some penetrating all the way to the core mantle boundary. The inner core itself appears to have a complex internal structure, with different regions rotating at slightly different rates. Most surprisingly, seismic imaging has revealed massive structures at the base of the mantle that don't fit any simple model of how Earth's interior should behave. These large, low shear velocity provinces, beneath Africa and the Pacific, are thousands of kilometers across, and appear to have been stable for hundreds of millions of years, yet their origin and composition remain mysterious. Recent improvements in seismic imaging have begun to reveal even finer details. Scientists can now track how individual earthquake waves change as they pass through the inner core over periods of years, revealing that the solid center of our planet is rotating slightly faster than the surface, and that this rotation rate has been changing in ways no one expected. While seismologists map Earth's interior structure, other scientists use electromagnetic methods to probe the planet's electrical and magnetic properties. Magnetotelluric surveys measure how Earth's magnetic field induces electrical currents in the ground, revealing the distribution of conductive and resistive materials at depths ranging from meters to hundreds of kilometers. These measurements can map underground water resources, locate ore deposits, and image magma chambers beneath volcanoes. Ground-penetrating radar can image buried structures, ancient riverbeds, and archaeological sites without disturbing the surface. Airborne magnetic surveys detect subtle variations in Earth's magnetic field that reveal hidden geological structures and mineral deposits. But perhaps the most exotic tool for studying Earth's interior involves particles that barely interact with matter at all: neutrinos. The IceCube Neutrino Observatory, buried beneath 2 kilometers of Antarctic ice, consists of more than 5,000 optical sensors spread throughout a cubic kilometer of the clearest ice on Earth. This massive detector captures the faint flashes of light produced when high-energy neutrinos, ghostly particles created in nuclear reactions, occasionally interact with atoms in the ice. Most neutrinos pass through Earth as if it weren't there. Trillions of them stream through your body every second without you noticing. But by detecting the rare interactions that do occur, IceCube can study neutrinos that have traveled through Earth's core from the other side of the planet, potentially revealing details about conditions in Earth's center that no other technique can access. The observatory has already detected neutrinos from distant galaxies, proving that these cosmic messengers can provide information about the most energetic processes in the universe. Future experiments may use neutrinos to study the composition and temperature of Earth's core directly, answering questions about the origin of our planet's magnetic field and the processes that have shaped its evolution. Ocean exploration has been revolutionized by remotely operated vehicles and autonomous underwater vehicles that can dive to depths where the pressure would instantly crush any human explorer. These robotic submarines carry cameras, sampling equipment, and sensors into environments as alien as anything we might find on other planets. The deep ocean trenches, which plunge more than 11 kilometers below sea level, remain largely unexplored, despite covering vast areas of Earth's surface. The few expeditions that have reached these depths have discovered ecosystems unlike anything found elsewhere on our planet. In the deepest parts of the Mariana Trench, where water pressure exceeds 1,000 times atmospheric pressure at sea level, unique species of amphipods, xenophyophores, and bacteria thrive in conditions that would be instantly lethal to surface life. Hydrothermal vents on the ocean floor support entire ecosystems based on chemosynthesis rather than photosynthesis. Giant tube worms without digestive systems rely on symbiotic bacteria to convert hydrogen sulfide and other chemicals into organic compounds. These deep-sea communities may provide clues about how life first evolved on Earth and where it might exist on other worlds with subsurface oceans. Advanced submersibles can now spend months at a time exploring the deep ocean, mapping previously unknown underwater mountain ranges, documenting volcanic activity on the seafloor, and collecting samples from environments that remain more mysterious than the surface of Mars. Mass spectrometry has reached levels of precision that allow scientists to analyze individual atoms in microscopic samples, revealing information about the conditions under which those atoms formed. Modern instruments can determine the age of rocks by measuring the decay products of radioactive elements, calculate the temperatures at which minerals crystallized, and identify the sources of materials that traveled across continents or ocean basins. Isotope analysis of ancient shells, bones, and teeth reveals not just when organisms lived, but what they ate, where they traveled, and what the climate was like during their lifetimes. Carbon isotopes in tree rings and ice cores provide year-by-year records of atmospheric carbon dioxide concentrations, extending back thousands of years. Oxygen isotopes in marine fossils reveal ancient ocean temperatures with precision that rivals modern thermometers. These techniques have revealed that Earth's climate has fluctuated dramatically throughout history, with ice ages and warm periods alternating in cycles controlled by variations in Earth's orbit around the sunday. They've shown that major volcanic eruptions can affect global climate for years or decades, and that past changes in atmospheric carbon dioxide concentrations correlate strongly with global temperature changes. Computer modeling has become so sophisticated that scientists can simulate the behavior of Earth's atmosphere, oceans, and ice sheets with enough detail to predict how these systems will respond to different scenarios of future greenhouse gas emissions. Climate models now include interactions between the atmosphere, oceans, land surface, ice sheets, and even vegetation, creating virtual Earths that behave remarkably like the real planet. These models have been crucial for understanding how human activities are affecting Earth's climate system. They've shown that the rapid increase in atmospheric carbon dioxide concentrations over the past century is unprecedented in at least 800,000 years of geological history, and that the resulting climate changes are likely to persist for centuries, even if greenhouse gas emissions are reduced. But modeling isn't limited to climate prediction. Scientists use computer simulations to understand how tectonic plates move, how earthquakes rupture along fault systems, how volcanic eruptions develop, and how impact craters form when asteroids strike Earth. These models allow researchers to test hypotheses about processes that occur too slowly, too dangerously, or on too large a scale to study directly. Laser interferometry has pushed the precision of Earth measurements to almost unimaginable levels. The Laser Interferometer Gravitational Wave Observatory uses laser beams to detect changes in distance smaller than 1/10,000th the width of a proton, a precision so extreme that it can detect gravitational waves created by colliding black holes billions of light-years away. This same technology is being adapted to study Earth's processes. Laser strain meters can detect ground deformation caused by Earth tides, AI, the slight stretching and compression of solid rock caused by the gravitational pull of the Moon and Sunday. These instruments are so sensitive they can measure how the rotation of Earth's core affects the planet's surface, revealing details about processes occurring thousands of kilometers beneath our feet. Quantum sensors now in development promise even more extraordinary capabilities. Quantum gravimeters could detect changes in gravity so minute they could map underground magma chambers in real time, potentially providing weeks or months of warning before volcanic eruptions. Quantum magnetometers could measure magnetic field variations with enough precision to image electrical currents in Earth's core, revealing details about the processes that generate our planet's magnetic field. Space-based telescopes have begun to study Earth from perspectives impossible from the ground. Satellites in special orbits can observe the same location on Earth's surface continuously, tracking changes in vegetation, ice cover, and urban development with unprecedented temporal resolution. Hyperspectral imaging satellites can identify specific minerals and chemical compounds from space, mapping the composition of Earth's surface in detail that was previously possible only through direct sampling. These orbital observatories have revealed that Earth's surface is far more dynamic than visible light images suggest. Thermal infrared sensors detect heat flow from volcanic regions, track wildfires as they spread, and monitor the urban heat island effect in major cities. Radar altimeters measure changes in ice sheet thickness, sea level, variations, and forest canopy height with centimeter precision. Perhaps most remarkably, some of these space-based instruments can detect changes in Earth's atmosphere, oceans, and land surface that precede earthquakes, volcanic eruptions, and other geological events. Satellites have observed anomalous heating in the atmosphere above earthquake epicenters days before major quakes occur, though the mechanism behind this phenomenon remains mysterious. Artificial intelligence and machine learning have begun to revolutionize how scientists analyze the vast amounts of data collected by these instruments. AI systems can identify patterns in seismic data that human analysts miss, recognize early warning signs of volcanic eruptions in satellite imagery, and predict earthquake aftershock sequences with remarkable accuracy. Machine learning algorithms trained on decades of climate data can identify subtle correlations between different Earth systems, revealing how changes in one region affect conditions thousands of kilometers away. These systems have discovered that Antarctic ice loss affects atmospheric circulation patterns over North America, that Amazon rainforest deforestation influences monsoon patterns in Asia, and that Arctic sea ice changes correlate with winter weather extremes in Europe and North America. But perhaps the most important capability of these new technologies is their ability to monitor Earth's processes continuously and globally. For the first time in human history, we have a real-time comprehensive view of how our planet operates as an integrated system. We can watch as water evaporates from tropical oceans, travels through the atmosphere, and falls as snow on distant mountain ranges. We can track how carbon moves between the atmosphere, oceans, land vegetation, and geological reservoirs. We can observe how energy from the sun drives atmospheric circulation, ocean currents, and the water cycle that supports all life on Earth. This global perspective has revealed that Earth operates as a single interconnected system where changes in one component can cascade through the entire planet. The tools that allow us to see the invisible have shown us that nothing on Earth happens in isolation. Every process is connected to every other process through networks of cause and effect that span the globe and operate across timescales ranging from minutes to millions of years. The machines that see the invisible have not only answered many of Earth's ancient mysteries, they've revealed new mysteries that previous generations of scientists never knew existed. The precision and scope of modern Earth observation have shown us that our planet is far more complex, dynamic, and interconnected than anyone imagined, with processes operating on scales from quantum to global, and timescales from microseconds to geological eons. Yet for all their remarkable capabilities, these tools have also revealed the limits of human understanding. The more precisely we measure Earth's processes, the more questions we discover. Every answered mystery reveals new puzzles waiting to be solved. The machines that see the invisible have given us unprecedented insight into how Earth works, but they've also shown us how much we still don't know about the planet we call home. Even with our remarkable arsenal of tools that can peer through continents and detect changes smaller than atoms, Earth guards its deepest secrets jealously. Our planet, after 4.5 billion years of existence, still poses questions that challenge our most sophisticated instruments and most advanced theories. These mysteries remind us that beneath the familiar surface of our world lies an alien realm that operates by rules we're only beginning to understand. The inner core of Earth, a solid sphere of crystallized iron and nickel spinning at the center of our planet, was discovered less than a century ago. Yet, it has already surprised scientists multiple times. For decades after its discovery in 1936, researchers assumed this metallic heart of Earth rotated at the same rate as the surface. Then, in the 1990s, seismic evidence revealed that the inner core spins slightly faster than the rest of the planet, gaining about 1/3 of a degree per year on the surface world above. This discovery raised immediate questions. What causes the inner core to rotate independently? How long has it been spinning faster? Does this differential rotation affect Earth's magnetic field or the length of our days? Scientists developed theories to explain the inner core's behavior. The swirling motions of liquid iron in the outer core, they reasoned, could drag the solid inner core along faster than the mantle and crust above. Electromagnetic forces generated by the interaction between the inner core's rotation and the magnetic field might provide the necessary torque. But in 2009, everything changed again. New seismic analyses revealed that the inner core had begun slowing down. By 2010, it was rotating at the same rate as the surface. Recent studies suggest it may now be spinning slower than the rest of Earth, the first time this has been observed since scientists learned the inner core could move independently. No one knows why this happened. The change appears to correlate with variations in the length of Earth's days, measured in milliseconds by atomic clocks. It might be connected to fluctuations in the magnetic field. Some researchers think it could be part of a regular cycle, with the inner core alternately speeding up and slowing down over periods of decades or centuries. But these are educated guesses. The truth is that the most fundamental part of our planet, AZP, its solid metallic heart, behaves in ways that confound our understanding of how planetary interiors should work. Above the inner core, in the liquid outer core where Earth's magnetic field is generated, other mysteries multiply. The geomagnetic field that protects us from deadly solar radiation isn't steady. It fluctuates constantly, growing stronger in some regions while weakening in others. The magnetic poles wander across Earth's surface, sometimes moving hundreds of kilometers in a human lifetime. Every few 100,000 years, on average, the entire field reverses, with magnetic north becoming magnetic south. Right now, Earth's magnetic field is weakening at an alarming rate. It has lost about 5% of its strength in the past century, a rapid change by geological standards. The rate of weakening is accelerating, and the magnetic North Pole is racing across the Arctic Ocean from Canada towards Siberia at speeds that have forced frequent updates to navigation systems worldwide. Some scientists think these changes signal that Earth is heading toward another magnetic reversal. Computer models suggest that the current weakening pattern resembles the early stages of past reversals preserved in the geological record. If this interpretation is correct, we might be witnessing the beginning of a process that could take thousands of years to complete and leave Earth's surface vulnerable to increased cosmic radiation. But other researchers argue that the current changes are just part of the normal variation in Earth's magnetic field, which has strengthened and weakened many times without reversing. The truth is that despite decades of study using the most advanced instruments available, we still don't understand the fundamental processes that control Earth's magnetic field well enough to predict its future behavior. Even more mysteriously, scientists have discovered that Earth itself hums with constant low-frequency vibrations that no one can fully explain. In 1998, researchers analyzing seismic data noticed something strange. Earth was continuously vibrating at frequencies so low they're inaudible to human ears. These vibrations, called Earth's background hum, oscillate at periods of several minutes and appear to be present everywhere on the planet's surface simultaneously. The amplitude of these vibrations is tiny, ground movements measured in billionths of a meter, but their persistence and global extent suggest they're caused by some fundamental process operating within Earth itself. Scientists have proposed various explanations. The vibrations might be caused by ocean waves transferring energy to the solid Earth through interactions with the seafloor. They could result from atmospheric pressure variations that compress and decompress the ground. Some researchers think they might be generated by convection currents in the mantle, or by gravitational interactions with the Moon and Sunday. But more than 2 decades after their discovery, the source of Earth's background hum remains unknown. The vibrations continue, a constant reminder that our planet operates according to processes we don't fully understand. Deep beneath Africa and the Pacific Ocean, seismic imaging has revealed 2 massive structures that challenge every theory of how Earth's interior should behave. These large, low-shear velocity provinces rise from the core mantle boundary like underground mountain ranges, extending 3,000 kilometers upward through the mantle, nearly halfway to Earth's surface. Each structure is larger than a continent. The African anomaly stretches from beneath the Atlantic Ocean to the Indian Ocean. The Pacific structure spans from Asia to the Americas. Both appear to be denser than the surrounding mantle rock, yet they've remained stable for perhaps billions of years, despite the convection currents that should mix and homogenize the mantle over geological time. These structures affect how seismic waves travel through Earth's interior, creating shadow zones where earthquake waves are delayed or blocked entirely. They appear to influence the formation of volcanic hotspots at Earth's surface, i.e., many of the world's largest volcanic regions lie above the edges of these deep structures. But what are they made of? How did they form? Why haven't they been mixed into the surrounding mantle by billions of years of convection? Some scientists think they might be remnants of the moon-forming impact that struck Earth 4.5 billion years ago, pieces of the impactor, or Earth's original mantle that have somehow survived at the base of the broom. mantle ever since. Others suggest they could be accumulations of dense material that has sunk to the bottom of the mantle over billions of years, like sediment settling in a pond. Recent studies hint that these structures might be slowly moving and changing shape, but their evolution occurs so slowly that we may need decades of additional observations to understand their behavior. For now, they remain enigmatic features of Earth's deep interior, kind of sigh, continental-sized mysteries hiding in plain sight beneath our feet. Closer to the surface, other puzzles emerge from the interaction between Earth's interior and its outer layers. The Yellowstone supervolcano sits above a mantle plume that shouldn't exist according to current models of how Earth's interior convects. This plume appears to rise from deep in the mantle, possibly from the core mantle boundary itself, yet it's located in the middle of the North American continental plate, rather than at a plate boundary where such features are expected. Yellowstone has erupted catastrophically 3 times in the past 2.1 million years, each time releasing enough volcanic material to bury half of North America under meters of ash. The most recent eruption, 640,000 years ago, created a caldera 70 kilometers across and affected climate worldwide. Seismic imaging shows that a massive chamber of partially molten rock still exists beneath Yellowstone, extending from the surface down to depths of at least 50 kilometers. The chamber is gradually cooling and crystallizing, but it remains hot enough to drive the geysers, hot springs, and ground deformation that make Yellowstone famous. The question that haunts scientists is, when will Yellowstone erupt again? Statistical analysis of the timing of past eruptions suggests the next catastrophic explosion is overdue. The intervals between the 3 known supereruptions were roughly 800,000 years and 660,000 years. If this pattern continues, the next eruption should have happened already. But other evidence suggests that the Yellowstone system might be winding down rather than building toward another catastrophic explosion. The volume of volcanic material has decreased with each successive eruption. Recent volcanic activity in the region has been relatively small scale, involving normal eruptions rather than caldera-forming explosions. The truth is that we don't understand the deep processes that drive supervolcanic eruptions well enough to predict when they'll occur. Yellowstone might erupt tomorrow, in 10,000 years, or never again. The uncertainty reflects our limited understanding of how mantle plumes interact with continental crust and what triggers the release of enormous volumes of magma that create supervolcanic explosions. Even the most familiar geological processes continue to surprise us with their complexity. Earthquakes, which seem like straightforward responses to stress build-up and release along faults, produce phenomena that no one can fully explain. Earthquake lights, glowing phenomena that appear in the sky before, during, or after major earthquakes, have been reported for centuries, but only recently confirmed through photography and video. These lights take various forms: aurora-like sheets of luminescence, ball lightning, flame-like columns rising from the ground, or diffuse glows that appear above fault zones. They've been documented before earthquakes in Italy, Japan, Peru, and other seismically active regions, but scientists struggle to explain how stress in rocks deep underground could produce visible light in the atmosphere. Some researchers think earthquake lights might result from electrical charges generated when rocks fracture under extreme stress. Others propose that electromagnetic fields created by moving fault blocks could ionize gases in the atmosphere. Still, others suggest that the lights might be caused by methane or other gases released from the ground during earthquakes. But none of these explanations fully accounts for all the observed characteristics of earthquake lights. Their sporadic appearance, varied forms, and timing relative to earthquake activity remain mysterious. The phenomenon reminds us that even processes we think we understand, like how rocks break when stressed beyond their limits, continue to produce surprises. In the deep ocean, where most of Earth's surface remains unexplored, other mysteries multiply. Strange sounds recorded by underwater microphones include periodic low-frequency noises that don't match any known source. The bloop, a powerful ultra-low frequency sound detected by hydrophones in the Pacific Ocean in 1997, was initially thought to be produced by some unknown biological source. Later analysis suggested it might be caused by ice movement in Antarctica, but similar unexplained sounds continue to be recorded in ocean basins around the world. Deep-sea creatures display behaviors and physiological adaptations that challenge our understanding of the limits of life. Glass sponges in the deep Pacific grow to enormous sizes and appear to live for thousands of years, yet they thrive in environments with minimal food sources and no sunlight. Deep-sea fish display electrical properties that allow them to communicate and navigate in absolute darkness, using mechanisms that remain poorly understood. The deep ocean floor itself exhibits features that don't fit simple models of how seafloor spreading and plate tectonics should work. Massive underwater landslides have carved channels hundreds of kilometers long across abyssal plains. Mysterious circular depressions, some dozens of kilometers across, dot the seafloor in regions where no obvious geological process should create such features. Recent discoveries have revealed that the boundary between Earth's crust and mantle, ISBA, the Mohorovičić discontinuity, or MOHO, isn't a simple uniform layer as once thought. In some regions, the MOHO appears to be missing entirely. In others, it exists at different depths than predicted by plate tectonic theory. These discoveries suggest that the fundamental structure of Earth's outer layers is more complex and variable than our models assume. The processes that create and modify the boundary between crust and mantle might operate differently in different regions, influenced by factors we don't yet understand. Perhaps most unsettling of all, recent studies suggest that some of Earth's most fundamental characteristics might be changing in ways we didn't expect. The length of Earth's days has been increasing by about 1.7 milliseconds per century due to tidal friction from the Moon, but recent measurements show that this trend has reversed. Days are now getting slightly shorter, possibly due to changes in Earth's internal structure or the distribution of mass within the planet. Earth's rotation axis wobbles in complex patterns that reflect the movement of mass within the planet. Changes in ice distribution, groundwater storage, and ocean currents affect how Earth spins, creating variations in the length of days and the position of the geographic poles that we're only beginning to understand. These discoveries reveal that Earth operates as an integrated system, where processes in the deep interior, the oceans, the atmosphere, and even the ice sheets are all connected through complex feedbacks. Changes in one component can affect all the others in ways that are often difficult to predict. The questions that haunt Earth's deep places remind us that our planet remains, in many ways, an alien world. Despite centuries of scientific investigation and decades of sophisticated monitoring, we still don't understand the fundamental processes that make Earth unique among the planets we've studied. Every answered question reveals new depths of complexity. Every technological advance shows us phenomena we never suspected existed. Every measurement with improved precision uncovers variations and behaviors that challenge our theoretical understanding. The mysteries that persist in Earth's deep interior, in its magnetic field, in its seismic behavior, and in its interactions with space, remind us that we live on a planet that continues to surprise us. After 4.5 billion years of existence, Earth still has secrets waiting to be discovered, processes waiting to be understood, and questions waiting to be asked. These enduring mysteries aren't failures of scientific investigation. They're reminders of the incredible complexity and dynamism of the world we call home. They point toward frontiers of discovery that will challenge future generations of Earth scientists and reveal new aspects of how planets work, how life persists in extreme environments, and how integrated systems evolve over geological time. The questions that haunt the deep promise that Earth's story is far from over and that our understanding of this remarkable planet will continue to evolve as we develop new ways to probe its secrets and new frameworks for interpreting its signals. The next frontier of Earth exploration pushes beyond the current limits of imagination, promising discoveries that will revolutionize our understanding of how planets work and where life can exist. Within the next decade, humanity will achieve feats that previous generations of Earth scientists could only dream about, drilling directly into Earth's mantle, detecting gravitational changes smaller than the mass of a butterfly, and witnessing volcanic eruptions from inside the magma chamber itself. These aren't distant fantasies. They're projects already under development, technologies being tested, and missions being planned. The tools that will unlock Earth's remaining secrets are being built in laboratories around the world, and they promise to reveal aspects of our planet's behavior that we've never been able to observe directly. Japan's ambitious scientific drilling project represents perhaps the most audacious attempt to probe Earth's interior since humans first looked up at the stars and wondered what lay beyond. The plan, scheduled for completion by 2028, aims to drill through 6 kilometers of oceanic crust to reach the mantle itself, the layer of hot, flowing rock that makes up 84% of Earth's volume but has never been sampled directly. This isn't just an engineering challenge, it's an attempt to answer fundamental questions about how planets form and evolve. The mantle contains the chemical fingerprints of Earth's formation 4.5 billion years ago. It holds clues about how water and other volatile compounds were incorporated into our planet during its early history. It may preserve evidence of the moon-forming impact and other catastrophic events that shaped Earth's early development. Drilling to the mantle requires overcoming obstacles that have defeated previous attempts. The temperature at the crust-mantle boundary exceeds 1,000 degrees Celsius, hot enough to melt most drilling equipment. The pressure is enormous. The drill must penetrate through layers of rock with different hardnesses and chemical compositions, each presenting unique challenges. But the potential rewards justify the enormous technical and financial investment. Direct samples of mantle rock will reveal the composition and structure of Earth's largest layer, with unprecedented precision. They may contain evidence of how the mantle convects, how chemical elements are distributed throughout Earth's interior, and how the deep Earth has evolved over billions of years. The drilling project will also test whether life can exist in Earth's deep interior. Microbes have been found living in rocks several kilometers below the surface, surviving on chemical energy in environments with no sunlight and extreme conditions. If life exists near the mantle boundary, it would expand our understanding of the limits of biology and the potential for life elsewhere in the solar system. While engineers prepare to drill into Earth's depths, other scientists are developing quantum sensors that will detect changes in gravity so minute they could revolutionize our ability to predict volcanic eruptions and earthquakes. Quantum gravimeters use the wave-like properties of atoms to measure gravitational acceleration with precision that exceeds anything previously possible. These instruments can detect changes in gravity equivalent to the mass of a large building moving several kilometers underground. When deployed around active volcanoes, they could provide real-time maps of how magma moves beneath the surface, potentially giving weeks or months of warning before eruptions reach the surface. The same technology could monitor groundwater resources, track the movement of underground oil and gas reserves, and detect the formation of sinkholes before they collapse. Quantum gravimeters could map the internal structure of ice sheets, revealing how quickly they're melting and where they're most vulnerable to collapse. Perhaps most remarkably, networks of quantum gravimeters could detect the gravitational waves produced by earthquakes, ripples in space-time itself, created when massive amounts of rock suddenly shift position. This capability would provide a completely new way to study earthquake processes and might reveal early warning signs that precede major seismic events. The proposed Earth Observatory satellite constellation represents another quantum leap in our ability to monitor planetary processes. These satellites will measure Earth's magnetic field with unprecedented precision, potentially revealing why the field is currently weakening and when the next magnetic reversal might occur. The magnetic field measurements will be so precise they could detect the electrical currents flowing in Earth's core, providing direct information about the processes that generate our planet's magnetic shield. The satellites might reveal whether the current weakening of the magnetic field is part of a natural cycle or represents something more unusual. Understanding Earth's magnetic field behavior is crucial for predicting how it will respond to future changes in the planet's interior. It's also essential for protecting technology from magnetic storms and understanding how planets like Mars lost their magnetic fields and atmospheric protection. Scientists are preparing to deploy instrumentation that will monitor Earth's interior processes in real time, with resolution and scope that far exceeds current capabilities. Fiber optic cables laid on the ocean floor can detect seismic waves, ocean currents, and temperature changes across entire ocean basins. When earthquakes occur, these cables record the passage of seismic waves with spatial resolution measured in meters rather than the hundreds of kilometers typical of traditional seismic networks. Underground laboratories are being constructed in deep mines and tunnels, where sensitive instruments can operate without interference from surface noise and vibrations. These facilities will house detectors that can measure Earth's rotation variations, gravitational changes, and seismic waves with precision that approaches the fundamental limits imposed by quantum mechanics. The development of advanced materials will enable exploration of environments that have been completely inaccessible to human technology. Ceramic composites that can withstand temperatures exceeding 2000 degrees Celsius will allow probes to be dropped directly into volcanic conduits, providing the first direct observations of conditions inside active magma chambers. These volcanic probes will measure temperature, pressure, gas composition, and magma flow rates from inside erupting volcanoes. They'll reveal how volcanic eruptions develop, why some volcanoes explode violently while others erupt gently, and what warning signs precede different types of volcanic activity. The data collected by these probes could revolutionize volcanic hazard assessment, potentially saving thousands of lives by providing more accurate predictions of when and how volcanoes will erupt. The measurements will also advance our understanding of how volcanic processes have influenced Earth's climate and atmospheric composition throughout geological history. Artificial intelligence and machine learning are already beginning to transform Earth science research, and their impact will accelerate dramatically in the coming decades. AI systems trained on decades of seismic data have discovered patterns that human analysts missed, revealing that Earth's core has multiple layers with distinct compositions and behaviors. Machine learning algorithms can process satellite imagery in real time, automatically detecting changes in ice cover, vegetation patterns, and urban development. These systems can identify early warning signs of natural disasters, track the spread of environmental damage, and monitor the health of ecosystems across the globe. Future AI systems will integrate data from thousands of different instruments and sensors, creating comprehensive models of how Earth operates as an integrated system. These models will be able to predict how changes in one part of the planet will affect conditions elsewhere, providing early warning of climate shifts, resource depletion, and natural hazards. The combination of AI analysis and quantum sensors will enable the detection of phenomena that are currently invisible to human observation. Quantum magnetometers could reveal electrical currents in Earth's core that correlate with changes in the magnetic field. Quantum accelerometers could detect minute changes in Earth's rotation that reflect mass movements deep in the planet's interior. Biotechnology is opening new frontiers in studying life in extreme environments. Genetic sequencing techniques can now identify microorganisms living in environments previously thought to be sterile, not deep underground, in hot springs, and in highly acidic or alkaline conditions. These studies are revealing that life exists in far more extreme conditions than previously imagined, with implications for understanding how life might exist on other worlds. Future missions will search for life in Earth's deepest environments, including the mantle boundary where temperatures and pressures approach the limits of what biology can tolerate. If life exists in these extreme conditions, it would suggest that habitable environments might be much more common throughout the universe than currently believed. Space-based observations of Earth will reach new levels of detail and temporal resolution. Hyperspectral imaging satellites will be able to identify specific minerals and chemical compounds from orbit, creating detailed maps of Earth's surface composition that update in real time. These observations will track how human activities are changing the planet's surface and reveal natural processes that operate too slowly to observe during human lifetimes. Gravitational wave detectors designed to study cosmic events will also monitor Earth's internal processes. The Laser Interferometer Gravitational Wave Observatory has already demonstrated that it can detect seismic waves from major earthquakes. Future generations of these instruments will be sensitive enough to monitor reported continuous deformation of Earth's crust, providing early warning of volcanic eruptions and major seismic events. The next generation of ocean exploration vehicles will be capable of spending years in the deep ocean, autonomously exploring areas that have never been visited by humans. These vehicles will carry advanced analytical equipment that can identify new species, map underwater geological features, and monitor changes in deep ocean environments in real time. Swarms of small, intelligent probes will be deployed throughout the ocean basins, creating a global monitoring network that can track everything from deep ocean currents to the migration patterns of marine life. This network will reveal how the ocean system responds to climate change and how deep ocean processes influence global weather patterns. Perhaps most exciting of all, the integration of all these technologies will provide the first comprehensive, real-time view of Earth as a complete system. We'll be able to watch how energy flows from Earth's core to its surface, how materials cycle between the interior and the atmosphere, and how life interacts with geological processes on a planetary scale. This integrated view will reveal connections between Earth's systems that we've never been able to observe directly. We'll see how changes in the core affect the magnetic field, how magnetic field variations influence atmospheric chemistry, and how atmospheric changes affect ocean circulation and climate patterns. The tools being developed for Earth exploration will also advance our ability to study other planets. Quantum sensors designed to map Earth's interior could be adapted for missions to Mars, Venus, and the moons of Jupiter and Saturn. Techniques for studying life in Earth's extreme environments will guide the search for life elsewhere in the solar system. As we develop more sophisticated ways to monitor and understand Earth, we're also discovering that our planet's behavior is more complex and interconnected than we ever imagined. Every new measurement reveals additional layers of complexity, additional feedback loops, and additional ways that different parts of the Earth system influence each other. This growing understanding of Earth's complexity has profound implications for how we think about humanity's role in planetary processes. We're learning that human activities now influence Earth systems on the same scale as major geological forces. The carbon we're adding to the atmosphere, the water we're extracting from underground aquifers, and the changes we're making to land surfaces are all affecting global-scale processes that operate on geological timescales. Future Earth monitoring systems will track these human influences with the same precision they use to monitor natural processes. We'll be able to see exactly how human activities are changing the planet and predict what those changes will mean for Earth's future evolution. The next frontier of Earth exploration isn't just about answering scientific questions, it's about understanding our role as participants in Earth's ongoing story. The tools that will reveal Earth's remaining secrets will also show us how to be better stewards of the only planet we know that harbors life. Tomorrow's Earth speaks louder because we're developing better ways to listen. The whispers from our planet's deep interior are becoming conversations. The mysteries that have puzzled scientists for centuries are becoming solvable problems. And the questions that have driven human curiosity about our world are leading to answers that reveal even grander questions waiting to be explored. The future of Earth science promises discoveries that will fundamentally change how we understand planets, life, and our place in the universe. But perhaps most importantly, it promises to reveal the full beauty and complexity of the remarkable world we call home. Earth's unanswered questions reveal a profound truth that transcends any individual mystery or unsolved puzzle. Our planet operates as a single, breathing entity, where every component affects the whole in ways so intricate and interconnected that we may never fully comprehend them all. This isn't a failure of scientific inquiry, he say. It's the recognition that we live on a world of such extraordinary complexity that each answer we discover opens doors to rooms full of new questions. The magnetic field generated in Earth's churning outer core doesn't just shield us from deadly solar radiation, it influences atmospheric chemistry at heights of hundreds of kilometers above the surface. When solar storms interact with our magnetic field, they create cascading effects that ripple through the entire Earth system, disrupting satellite communications, altering the chemistry of the upper atmosphere, affecting the formation of clouds, and even influencing the behavior of migrating animals that navigate using magnetic cues. These connections between Earth's deep interior and its surface environment reveal something remarkable. Processes occurring thousands of kilometers beneath our feet directly affect the air we breathe and the climate that shapes our daily lives. Plate tectonics, driven by convection in the mantle, does far more than move continents and create mountain ranges. The cycling of ocean floor through subduction zones regulates the chemistry of seawater and the composition of the atmosphere over millions of years. When oceanic crust dives into the mantle at deep ocean trenches, it carries with it water, carbon dioxide, and other compounds that have been dissolved from surface rocks and incorporated into marine sediments. This subducted material eventually returns to the surface through volcanic eruptions, but the process takes millions of years and involves complex chemical transformations deep within Earth's interior. The carbon cycle that regulates Earth's climate operates through this geological recycling system, removing carbon dioxide from the atmosphere when rocks weather and returning it through volcanic emissions. Without plate tectonics, Earth's climate would have become permanently frozen or permanently overheated billions of years ago. The movement of tectonic plates provides a thermostat that has maintained conditions suitable for liquid water and life for nearly 4 billion years, a span of time that encompasses most of Earth's history. Deep ocean currents, powered by temperature and salinity differences created when water evaporates in tropical regions and freezes in polar areas, distribute heat around the globe in patterns that control weather and climate. The Gulf Stream carries warm water from the Caribbean to northern Europe, making the climate there much warmer than other regions at similar latitudes. The Antarctic Circumpolar Current connects the Atlantic, Pacific, and Indian Oceans, mixing their waters and distributing nutrients that support marine ecosystems worldwide. These currents operate on multiple timescales simultaneously. Surface currents respond to daily and seasonal changes in wind patterns. Deeper currents reflect longer-term variations in water density that may take decades or centuries to propagate around the globe. The deepest currents, driven by water that sank to the ocean floor in polar regions, may take more than 1,000 years to complete their circulation through the world's ocean basins. Changes in any part of this circulation system affect all the others. When ice sheets melt, they add fresh water to the oceans, reducing salinity and potentially altering the density differences that drive deep ocean circulation. When atmospheric temperatures change, they affect evaporation rates and the strength of winds that power surface currents. The interconnectedness extends beyond the physical Earth to include life itself. Plants and animals don't just respond to environmental conditions, they actively participate in shaping those conditions through their metabolic processes, their physical structures, and their behaviors. Forests affect local and regional climate by recycling water through evapotranspiration, moderating temperature through shading, and influencing wind patterns through their effects on surface roughness. Marine organisms extract carbon dioxide from seawater to build their shells and skeletons, affecting ocean chemistry and the global carbon cycle. Soil microorganisms break down organic matter and release nutrients that support plant growth, while also producing gases that influence atmospheric composition. Even the timing of biological processes matters for global-scale systems. The seasonal growth and decay of vegetation in northern hemisphere forests creates annual cycles in atmospheric carbon dioxide concentrations that can be measured at monitoring stations around the world. The synchronized flowering of certain plant species affects regional patterns of precipitation and humidity. This interconnected machine has maintained conditions suitable for life through periods of dramatic change that would seem to threaten the stability of the entire system. Ice ages have repeatedly locked up enormous amounts of water in continental glaciers, lowering sea levels by more than 100 meters and dramatically altering ocean circulation patterns. Massive volcanic eruptions have changed atmospheric composition for years or decades, affecting global climate and the productivity of ecosystems worldwide. Asteroid impacts have instantaneously altered Earth's energy balance, triggering mass extinctions that eliminated most species and fundamentally reorganized ecosystems. Yet through all these upheavals, Earth's integrated systems have maintained the basic conditions necessary for life to persist and evolve. The mechanisms that provide this stability operate through feedback loops that span the entire planet. When atmospheric carbon dioxide concentrations increase, temperatures rise, but this warming accelerates the weathering of rocks that removes carbon dioxide from the atmosphere. When ice sheets grow, they reflect more sunlight back to space, causing additional cooling that promotes further ice growth. But this cooling also reduces evaporation from the oceans, eventually limiting the supply of moisture needed to sustain the ice sheets. These feedback mechanisms usually act to moderate changes rather than amplify them, but they can be overwhelmed when the system is pushed beyond certain thresholds. The challenge for scientists studying Earth's behavior is that we often don't know where these thresholds lie until we've crossed them. Understanding Earth's integrated behavior has become even more crucial as we've realized that human activities now operate on the same scale as many natural Earth system processes. The amount of carbon dioxide we're adding to the atmosphere each year equals the output of a moderate volcanic eruption continuing indefinitely. The amount of water we're extracting from underground aquifers affects global sea level. The changes we're making to land surfaces influence regional climate patterns and the global water cycle. We have become a geological force, participants in Earth's story, rather than just observers of it. This realization brings both responsibility and opportunity. We can affect Earth's future evolution, but we can also learn to work with natural Earth system processes rather than against them. As we search for life on other worlds, Earth's mysteries become even more precious and significant. Every unanswered question about how our planet maintains conditions suitable for life potentially holds keys to understanding how common such worlds might be elsewhere in the universe. The discovery that life exists in Earth's most extreme environments, ES9, in boiling hot springs, in acidic volcanic lakes, in the high-pressure depths of ocean trenches, in rocks kilometers below the surface, suggests that the range of potentially habitable environments in the universe might be much broader than we previously imagined. But the more we learn about the conditions that allow life to thrive on Earth, the more we realize how remarkable our planet truly is. The combination of liquid water, a protective magnetic field, plate tectonics that regulates climate, and the dozens of other factors that make Earth habitable might be extremely rare in the universe. Or perhaps the processes that create Earth-like conditions are more common than we think, operating through mechanisms we haven't yet discovered on worlds we haven't yet learned to observe properly. The mysteries that remain unsolved on our own planet remind us how much we still don't know about how planets work and what makes them capable of supporting life. Each unanswered question about Earth represents a frontier of discovery that could transform our understanding of planetary science, biology, climate, and our place in the cosmic story. Why does Earth's inner core sometimes speed up and sometimes slow down? What triggers the reorganization of Earth's magnetic field during reversals? How do life and geological processes interact to maintain stable conditions over billions of years? These questions don't exist in isolation. They're all connected through the integrated web of processes that makes Earth the dynamic living world we inhabit. Understanding any one of them fully would require understanding how it connects to all the others, which may be impossible given the complexity of the system we're trying to comprehend. But this impossibility isn't a limitation, it's what makes Earth's story eternally fascinating. We will never run out of questions to ask about our planet, because each answer reveals new aspects of its behavior that we didn't know existed. We will never fully predict Earth's future, because its systems operate through interactions too complex for any model to capture completely. The story of Earth's mysteries is ultimately the story of us, curious beings on a curious world, forever asking questions of the ground beneath our feet and finding that it always has more to teach us. We exist because Earth found solutions to seemingly impossible challenges over billions of years. We are here because our planet proved remarkably resilient in the face of cosmic catastrophes, climate upheavals, and biological crises that might have ended the story of life entirely. The oxygen in every breath we take was produced by ancient organisms that transformed Earth's atmosphere. The water we drink has circulated through countless cycles between oceans, ice sheets, atmosphere, and underground reservoirs. The ground we walk on has travelled thousands of kilometres from where it formed, carried by the patient motion of tectonic plates. We are made of elements forged in the hearts of dying stars, assembled into a living planet through processes that took billions of years to complete, sustained by systems so intricate that we're only beginning to understand how they work. We are Earth's way of asking questions about itself. The forever mystery isn't any single unanswered question about how our planet works. It's the recognition that Earth's story is still being written, that new chapters are being added through processes operating right now beneath our feet, in the depths of the oceans, in the core of the planet, and in the interactions between life and environment that continue to shape our world's future. Every time we think we understand how Earth works, our planet surprises us with new phenomena, unexpected connections, and behaviors that don't fit our models. This isn't a failure of science. It's a reminder that we live on a world of infinite complexity and beauty, a planet that rewards curiosity with discoveries that exceed our wildest expectations. The whispers from Earth's deep places have become conversations, but the conversation is far from over. Our planet still has stories to tell, mysteries to reveal, and questions to pose that will challenge future generations of scientists and continue to expand our understanding of how worlds work, how life persists, and how remarkable our cosmic home truly is. In the end, Earth's greatest mystery might be that a planet capable of supporting curious beings like us exists at all. That in a universe dominated by empty space and lifeless rocks, there emerged a world where granite can wonder about its own origins, where water can question its own flow, and where the products of stellar alchemy can contemplate the cosmos that created them. We are Earth's mystery to itself, and Earth is our forever mystery, an enduring source of questions that will continue to inspire, wonder, and drive discovery as long as curious minds exist to ask them.